Hello, welcome back to my channel. Today I want us to look at magnetic field, and of course, as we are just few days away from the JAMB exam, I'll advise you to take this topic serious. Magnetic field. Now, by this magnetic field, we want to look at the charge, the magnetic force on the charge when a charge moves in a magnetic field. Now, before we start, if you have not subscribed to this channel, please hit the subscribe button, hit the like button, and then share this video with your friends. Now, let us start. Magnetic field. We ask ourselves, what is a magnetic field? Just like every other field, we have electric field, we have the gravitational field, we have electric field. Today, we just want to look at the magnetic field. The magnetic field is nothing but a region around a magnet in which the effects or the influence of a magnetic force can be felt. So it's just a region around the magnet in which its effects, in which the effect of magnetic force can be felt. Now we want to look at if this is, let's say, a magnetic field. If this is a magnetic field, let's just take it like this. If it's a magnetic field, now we want to look at the charge moving in a field. So in this topic, we're going to concentrate just on the charge. Now, if this charge is moving in a field, and of course, we know that once a charge starts moving, electricity is generated. Now, our interest here is to look at that electricity, how electricity is generated here. And of course, it is this field, this magnetic field, that generates magnetic force. So it is the magnetic field that generates a magnetic force. So it is this force that pushes this charge to start to move. And of course, once they move, current is flowing. Now we have, in this field, we can have a vector here. This vector, we can call it B. This vector B. Of course, this vector B is just the strength of this field, the field strength, the magnetic field strength, which is B, otherwise known as the flux density. So we say B is the flux or magnetic flux density. Now, assuming we have here, this is a we can have here as our force. Now, if a charge is free to move in this field, now if this charge is moving, it can move with a certain speed v. So we have 1, 2, 3. These are the three major parameters here. Now, if a charge is moving, either it is moving in the direction of the field. If it is moving in the direction of the field, that means it is moving horizontally. Now, if it is moving perpendicular to the field, so we're going to discuss two things. Perpendicular. So perpendicular, permit me to use this to represent perpendicular. So if a charge is moving perpendicular to the field, that means it is moving at 90 degrees. That means if the charge is moving in this direction now, if the charge is moving in this direction, that means it is moving perpendicular to the field or the flux density. Now, it can also move parallel to, so parallel, the first one is perpendicular, the second one is parallel to the field. So it is either it's moving perpendicular to the field or it is moving parallel to the field. But I want you to note two things here. If it is moving parallel to the field, of course, this is 0 here. If it is moving parallel to the field, that means the angle of inclination will now come in now. So we have the angle of inclination, which is the angle between the velocity and the field. So in this case, we can have that the B is the flux density, V is the velocity, and of course the velocity is measured in meters per second, while the flux density or the field, the magnetic induction, either you call it flux density or you call it the magnetic induction, it is measured in Weber per meter squared, or otherwise known as Tesla, capital T. So if you see it in Weber per meter squared, you can also see it in Tesla. And of course, the what you're going to see in Tesla is the magnetic flux density or the magnetic induction. Now, this F here is the, of course, we've measured it before, magnetic force. Remember, it is that force generated by this field that pushes the charge to flow. Now we have that F is the force, magnetic force, measured in newtons. Now the next thing, now remember, we have charge moving here, so that charge we can have the charge. So the charge, it can either move parallel to the plane, parallel to the field, or perpendicular to the field, or it can also move in any of these direction. But here remains our v, the velocity with which this charge is moving. So we now have that Q, or most textbooks will always use E. Either you have it as E or you have it as Q. It is represented as the charge, and of course this charge is measured in coulombs. So we are going to look at assuming this magnetic force, if the charge is moving either in any of these directions, parallel to the plane or perpendicular to the plane. Now I forgot to mention that, yes, if the charge is moving perpendicular to the plane, that means the electric force, the magnetic force is maximum here. So in this case now, the electric force, the magnetic force, please, magnetic force is maximum at this point. So at this point, it is maximum. Now, if the charge is moving parallel to the plane, then the electric force there, the magnetic force there, please, the magnetic force there is minimum at this point. So at this point, it has no magnetic force here. It only has magnetic force at this point. Now let us show it. So we can always say that, yes, the force, the magnetic force, when a charge is moving perpendicular to the field, is F is equal to QV, then we have B sine theta. Now since theta is at this point, when it is moving perpendicular to the plane, it is 90 degrees. Now since it is 90 degrees, sine 90, if you press sine 90 in your calculator, sine 90 will give us 1. Since it is 1, this equation cannot be reduced to give us that F is equal to QVB. Now because sine, if this is 90, sine 90 is 1. 1 times the whole of this will still give us, this is what it will give us. So the only condition that we use this formula is when the charge is moving perpendicular to the plane, or if they say from the question it is moving at 90 degrees, you are free to use this. If you still use this one, you are okay. So we can have this one as equation 1 and this one as our equation 2. So these two are the same, but preferably if theta is 90 degrees, you use this. If you use this, it will still return you to this. Now we look at the second option here. if the charge is moving in the same direction with the field, that means theta here is 0 or 180 degrees, because angle on a straight line is 180 degrees. So in that case, this equation F is equal to QVB sine theta will reduce to, at the end of everything will give us 0, because sine 90, if we have sine theta as 0, we have sine 0 is 0, 0 times b times this times this. Therefore, at this point, if the charge is moving parallel to the field or in the direction of the field, it does not have the magnetic force. The magnetic force there is 0. Now, let us take one or two calculations to add the flesh to what we have just discussed. A proton moving with a speed of 1 times 10 to the power 6 meters per second through a magnetic field of 1.0 Tesla experiences a magnetic force of magnitude 8 times 10 to the power minus 14 newtons. The angle between the proton's velocity and the field is dash. Of course, it must be one of these options here. This question came out in JAMB 2005, and it has been occurring, since that time, though on a cloned, they cloned the question. Now, they say one electronic charge is 1.6 times 10 to the power minus 19 coulombs. So we have a solution. Now, the first thing we do is to bring out the parameters given to us. Now from here, they said that the speed V is 1 times 10 to the power 6 meters per second. The flux density here, B, is 1.0 Tesla. The magnetic force experience, which is F, is 8 times 10 to the power minus 14 newtons. Then the angle between the proton's velocity and the field is what we are looking for. Now, in this case, we have that, of course, the formula to apply is F is QVB sine theta. Now, at this point, we're going to make sine theta the subject. If you make sine theta the subject, we have that sine theta is equal to F all over, now these three, QVB, which will give us that sine theta is equal to F. Now we'll bring F out. F is 8 times 10 raised to the power minus 14 all over Q. Now the Q is, of course, it is 1.6 times 10 raised to the power minus 19 multiplied by V, the velocity, which is 1 times 10 raised to the power 6 multiplied by the field flux, the flux there, which is 1 Tesla. Now we still have that sine theta is equal to, now 8 times 10 to the power minus 14. Remember the rules, the law of indices. Now, since we are dealing with this, all we need to do is these index numbers, send these index numbers up. And of course, this one is minus. If it goes up, plus. If this one goes up, minus. So we have plus 19 minus 6 all over the base now. The base, which is 1.6 times 1 times 1, will still give us 1.6. Now, which will give us sine theta is equal to, now 8 divided by 1.6. 8 divided by 1.6 will give us 5. 5 times 10 raised to the power. Now, minus 14 plus 9 minus 6. Check your calculator there to give you minus 1. Now, we now have that, of course, 5 times 10 raised to the power minus 1 is equivalent to 0.5. In other words, we now have that sine theta is 0.5. Now, theta is the sine inverse of 0.5. And the sine inverse of 0.5 is 30 degrees. So, sine inverse of 0.5 will give us 30 degrees, which is option B. Okay, we will still take another one. Okay, we look at this second question, and this question says, calculate the magnitude of the force due to a magnetic field of 0.4 Tesla on an electron moving perpendicular to the field, with a speed of 4 times 10 raised to the power 6 meters per second. Now, this question came out in 2013, and then they say Q is this. Now, we have that solution. In this case, we need to pay attention to the details of this. We are looking for the magnetic force there. The magnetic field, the flux density there is 0.4 Tesla. Now, on an electron moving perpendicular, remember I told you earlier that if the charge is moving perpendicular to the field, that means the angle of inclination there is 90 degrees. Now, the speed of the field now is 4 times 10 raised to the power 6 meters per second. Now, how do we get our F? Now, of course, our F is equal to QVB sine theta. Remember, in this case now, we said sine 90 is 1. Or we can still use this, or we use a QR. We can say F is equal to QVB. If this and this can go. Okay, well, in this case, we now have the F. For the benefit of doubt, we can use this, which is equal to Q. The charge there is 1.6 times 10 raised to the power minus 19 multiplied by V, which is the speed, 4 times 10 raised to the power 6 multiplied by B, which is the flux density, 0.4 Tesla, times sine 90, which will give us, we, like as usual, multiply the bases first. If we multiply the bases first, we now have 1.6 times 4 times 0.4 times 10 raised to power minus 19, this one, plus 6 multiplied by sine 90, sine 90, which will give us 1.6 times 4 times 0.4 will give us 2.56 times 10 raised to power. Now, minus 19 plus 6 will give us minus 13. Remember, sine 90 is 1 times 1 will still return us with this. In other words, we can have that the magnetic force there is 2.56 times 10 raised to the power minus 13 Newton. So this is the magnetic force when the electron is moving perpendicular to the field. And let us look at another one. We look at this third question. This question says, a conductor of length 2 meters carries a current of 0.8 ampere while kept in a magnetic field of magnetic flux density 0.5 Tesla. The maximum force acting on it is dash. Of course, that question came out in 2000 in 2000 JAMB. So the option must be either of any of these options here. Solution. Now, all this while we have been dealing with magnetic force when the charge is moving at a certain speed. Now, from this question, it is just is kept in a magnetic field, and we have this is just a conductor from somewhere that is carrying a charge in this. Now, all we need to do is to x-ray this. We have that the length of that conductor is 2 meters. It is carrying current. The current now is 0.8 ampere, while kept in the magnetic field of flux density. Now, B there is 0.5 Tesla. Now, the magnetic force in this case is given as. All right, I forgot to give you from the equations there. When the charge is not moving with a particular speed, maybe you have current now, because of course current is charge in motion. Now we can always use that the magnetic force is given as the flux density multiplied by the current and then multiplied by L. Of course, L is the length of that conductor. So if we substitute into this equation, we now have that the magnetic force is equal to flux density 0.5 multiplied by the current it is carrying 0.8 ampere multiplied by the length of that conductor. The length of that conductor is given as 2. So if we do that calculation here, 0.5 multiplied by 0.8 multiplied by 2. At the end of the day, we'll now have that the magnetic force there is 0.8 Newton. And of course, it is option C. So option C is the right answer option. Please check out, you can refer to pre-50. If you get pre-50, JAMB pre-50, you will see as many questions as possible. We cannot exhaust them now, so we'll just take this last one, and that will be all. Okay. Last but not the least, a particle of charge Q and mass M, moving with a velocity V, enters a uniform magnetic field of strength B in the direction of the field. The force on the particle is dash. Now we have all these equations given to us, and the answer must be this. Now, to cut the whole story short, because they have said the question says it is moving in the direction of the field. So if the charge is moving, this is the direction of the field B, this is F. Now we have here as our V, here is theta. Remember what we said earlier, if the charge is moving in the direction of B, the whole thing, it doesn't have any force. It means that the theta there, it is minimum at that point. The force is minimum, meaning that sine theta is equal to 0, or 0, theta is equal to 0. Theta is 0, therefore sine 90, sine 0 will give us 0, or 100, sine 180 or sine 0 will give us 0. Everything multiplied by 0 will return us to 0. Therefore, the correct answer option there is this, because it is moving in the direction of the field. But if it's moving perpendicular to the field, then we can consider taking the calculations. All right, so this is where we'll draw the lesson to an end. Please feel free to check the link in the description down below. You will see our WhatsApp link. Click on that WhatsApp link and then join our WhatsApp class where we'll be holding the online classes every time. Please, I need your encouragement. If this video was helpful to you, please give it a like, hit the subscribe button, and then see you in my next video where I'll bring in to you the concept of transformers. Bye.